In section 16.5, we'll take a look at curl and divergence, which are two kinds of derivatives that we apply to three-dimensional vector fields. So all of the vector fields that are used in this section are going to be three-dimensional. Okay, so before we get to curl and divergence, let's quickly revisit the gradient vector field. So we can think of the gradient as a kind of derivative that takes a scalar function and produces a vector field. And also, in terms of the notation here, so what we can do is we can separate this upside down triangle symbol called del, so and the scalar function f, right? So if we think of del symbolically as a vector itself, but not like an ordinary vector, a vector operator. So symbolically, what it is each of the components is a partial derivative with respect to each of the variables x, y, and z. And what an operator means is that you apply it to functions. So, for example, if you write del f like this, so we think of del as, again, a vector and f as a scalar function. So writing del next to f can be thought of as kind of like scalar multiplication, right? So here, to scalar multiply this calculation here, the scalar f needs to be, each partial derivative needs to be applied to the scalar f. And then the result is itself a vector, a vector field. So again, if we separate the del operator with the scalar function f, when you write out the gradient like this, this is the calculation that we're familiar with, but you can think of it in terms of scalar multiplication. Okay, so now let's introduce the curl. The curl is a generalization of the derivative that's applied to three-dimensional vector fields and results in another three-dimensional vector field. And the curl can be calculated in terms of something like a cross product, right? So the formula for the curl is written out here. So you have a three-dimensional vector field whose components are p, q, and r. You calculate the curl as kind of like a cross product. So writing out the 3x3 determinant, right? So here we put del x, del y, and del z, right? So I mean, this is not an ordinary vector; it's a vector operator, right? But you can still symbolically write it out like this, with the three components p, q, r are written just below, and just perform the 3x3 determinant that you're familiar with, right? So for each component, you cross out the column and the row, and then it's a 2x2 subdeterminant, right? So del y applied to r minus del z applied to q. So that's exactly this thing here. If you remember, the middle term has an extra minus. So don't forget about this. So the middle term has an extra minus, and then you have the 2x2 subdeterminant crossing out the top row and the middle row. So it's del x applied to r minus del z applied to p, again with the extra minus here. And then finally, for k, it's del x applied to q minus del y applied to p. So this is the formula for the curl. And if you go back and think in terms of physics, if a vector field represents the flow of some kind of fluid, like air currents or water currents, then the magnitude of the curl can be thought of as measuring how much the fluid swirls around each point, and the direction of the vector tells whether the swirl is going clockwise or counterclockwise. Also notice that the k component of the curl has the partial derivative of q with respect to x minus the partial derivative of p with respect to y, which is exactly the same expression that appears in Green's theorem. So eventually, when we want to generalize the Green's theorem, will involve the curl. Okay, so that's the curl. Next, let's talk about the divergence. Again, this is a kind of derivative that's applied to a three-dimensional vector field, except the result this time is a scalar function, and the calculation can be thought of in terms of a dot product. So the formula is given here, right? So the divergence of the vector field f is del dot f, which is just the del operator dot product with the components p, q, r, right? So you apply each corresponding operator to the corresponding component. So del x applied to p, and then plus del y applied to q, and then plus del z applied to r. And then the result here is a scalar function. Again, if the vector field represents some kind of flow, then the divergence calculates the tendency for the fluid to collect or disperse at each point. Okay, so so again, these are the formulas for curl and divergence. So let's take a look at an example where we calculate each.